I'm Jeff Tilley. I'm a research associate at the University of North Dakota in the Odegaard School of Aerospace Sciences, and my poster deals with developing a low-cost unmanned aircraft system platform that you see right here for air and surface layer atmospheric measurements. One of the goals of these measurements is to try and get a better understanding of the lower atmosphere structure so we can understand how radars and LIDARs and other sensing devices that use electromagnetic energy as their means of measuring the atmosphere, how they are affected by these fine-scale structures that we often see in the lower atmosphere. The nice thing about this particular system is that components off the shelf. Our airframe here is actually something we got at a hobby store, and so the entire platform and the system here was very, very low cost compared to most unmanned aircraft platforms that are in use today for atmospheric or other applications. We did all of our measurements at a range in North Dakota. That's about 2 hours drive from our university location in Grand Forks, and we have a very flat prairie grass runway area that we're using. It's part of the National Guard facility that's out there. And there's a couple of ridges that we place observers on to watch the track of the UA as it goes around this particular airstrip up and down, getting measurements both in the horizontal and the profiles. And what we found is some interesting structure that isn't often depicted in other types of observations, like from radio signs. We see a lot of very fine-scale differences in the refractivity, which basically says that there's a lot of variation in how a radar beam might propagate in the horizontal after it leaves the transmitter. You can get three different types of propagation characteristics that we see here, and these observations capture them very well. We have a ducting regime. We have what's called a subrefraction regime, in which it bends less than might normally be expected for a standard atmosphere, and we have pretty typical standard refraction. And all of these results are from flights that we did just this past November. We've been working with our engineering school to develop these particular technologies for about the past year to year and a half, and we're very excited that we're seeing such good representation of structure that hasn't been seen before, but it's very consistent with other work that we've been doing there looking at radar propagation. So we're hoping to expand what we can do with this system, have another full season of observations in the summer. It's a little cold right now in North Dakota for that, but we're hoping to be able to do a lot more observing, get a lot more information on not only electromagnetic propagation environments, but just how the boundary layer behaves as well.